Okay, people, we continue where we left it. So remember where we left it. We said that we saw that neutrinos from the sun, from Barenboim neutrinos, the most energetic neutrinos, neutrinos above the MEVs, their survival rate was 30%. We are producing essentially a second mass eigenstate, while for low energy neutrinos, PP and beryllium-7 neutrinos, the survival rate is 60%, meaning that you are produced 70% in the first mass eigenstate, 30% in the second mass eigenstate, and we somehow concluded that maybe producing neutrinos in the very center of the sun was not the same as producing them in vacuum. And I stress that what I mean, as the result of that, I will show that in matter, you have different mass differences, and different mixing angles. But the meaning, you know already the meaning of that. This will mean that the flavor, the coordinate superposition of mass eigenstate associated to a given flavor changes if I'm in the middle of a dense medium or I am in vacuum, but we are going to explicitly calculate that and see how this changes. And for that, this effect was proposed independently by Wolfenstein and Smirnov and Mikheyev in the 80s, but we are going to solve that again in the two neutrino case, and we are going to show what happens in the three neutrino case afterwards. And for that, we need to start with what I call the neutrino evolution equation, which is nothing but the Schrödinger equation. You have seen this and call it the Schrödinger equation when you were doing quantum mechanics. And you already know that if I'm talking about the mass eigenstate basis, I said already many, many times, mass eigenstates are the asymptotic states of the Hamiltonian. They evolve in the phase. So you already know that in the mass eigenstate basis, the Hamiltonian must be diagonal. If it were not diagonal, the two equations wouldn't decouple. Okay, so you already know that this Hamiltonian in the mass eigenstate is diagonal because the two equations decouple and each neutrino evolve with the phase given by its energy, which is what you expect. So in the mass eigenstate basis, this is the Hamiltonian, so you know it's diagonal. If my neutrinos are extremely relativistic, the energy is essentially P. But remember that before we said that whatever was proportional to a global phase will die when calculating oscillation probabilities because the absolute value of a phase is equal to 1. We showed that before. What does it mean, this phase in Hamiltonian language? In Hamiltonian language, the analog of that will be anything proportional to the identity matrix will result in what? In a global phase, which eventually will die. So I will be able to, I will remove anything proportional to the identity matrix because I know that at the end of the day, it won't have any effect when calculating transition or survival probabilities. Okay, so I will expand this and throw away something proportional to the identity because I know it will have an effect. I don't have any need to do that. I could carry out the complete calculation, but as I'm gonna diagonalize a matrix by inspection, I need to do that. But you are welcome to try yourself to show that you can do it with Mathematica, to do with the full expression, and you are gonna get the same result. Okay, so this is my Hamiltonian in the mass eigenstate basis, but now I want to start introducing in a medium. In a medium, I have interactions. So I need to move to the flavor basis, and I do it by hitting left and right with a mixing matrix in this way. So this Hamiltonian gets this form. Let me remind you what I have done. This Hamiltonian, a diagonal Hamiltonian in the mass eigenstate, but you show me I can do that. I am not doing it with my finger, you see? Okay, so I'm really primitive, you know. So this Hamiltonian, which is diagonal in the mass eigenstate basis, has exactly this form in the flavor basis, but it's the same Hamiltonian, okay? So this means if in a couple of transparencies, I stumble across a Hamiltonian, which at least can formally written, but be formally written in this way, for some effective mixing angle and for some effective mass difference, I will immediately know that I have found already the asymptotic states of the Hamiltonian. okay? Because I know that whatever is written in this form, for an effective mixing angle and effective mass difference, fine. But whatever can be written in this form on the flavor basis has this form on the mass basis. Okay, so I already know that. Now let's start to this Hamiltonian, which is the Hamiltonian in vacuum, to start adding interactions. My neutrinos have charge current interactions and neutral current interactions. Okay, so charge current interactions are only enjoy or suffer or whatever for the electron neutrinos. In the sun, you have electron neutrinos, but you have electrons, but you don't have muons or taus. So only electron neutrinos are going to have charge current interactions. And of course, these are weak interactions. This means they are proportional to G Fermi. And of course, they are proportional to the number of targets you find on your way. Okay. So, of course, this is attractive for neutrinos and repulsive for antineutrinos. But you also have neutral current interactions. But neutral current interactions, we already said this many times, are flavor blind. These are neutral, okay? Are flavor. If they are flavor blind, this means they are the same for the three flavors, meaning that they are proportional to the identity matrix. Just forget about that. I don't even need to include that. Don't even bother because they won't play any difference. It's proportional to the identity. However, if I were to introduce in this game sterile neutrinos, I cannot do this game anymore. Because if I were to introduce sterile neutrinos, then the neutral current will distinguish between active and sterile neutrinos, and the contribution to the Hamiltonian will be proportional to the identity any longer. I can play this game as long as I have only active neutrinos involved into this game. Okay, so this is the contribution I need to include, but let me again remove a piece proportional to the identity just to make this easier to diagonalize. But as I said, you don't need to do that. You can do it, okay, and you will get exactly the same result using the first form and not the second. So if I include now both contributions, the vacuum contribution plus the interaction term, this is what I get. And of course, it would be fantastic if you can read this matrix in this way, because we know that if we write it in this way, it's automatically diagonal in the flavor basis, at least for some mass difference and for some mixing angle. And you can do that easily by this identification. But this identification teaches us a lot about what's going on. First of all, remember that we are assuming that the mass difference is different from zero to begin with. If the neutrinos were degenerate in mass, the mixing angle will be unphysical because any combination of mass eigenstate will be a mass eigenstate because they are degenerate in mass. So any flavor eigenstate will be also a mass eigenstate, okay? So if the masses were identical, any combination you want of mass eigenstate is a mass eigenstate and therefore is a flavor eigenstate. So we are assuming from scratch that this mass difference is different from zero. So the thing to learn from this identification is that there is a quantity, this combination of mass difference square times the sine of 2 times the mixing angle is an invariant quantity, meaning that it has the same value in a medium and in vacuum. This will mean that if my mixing angle was 0 to begin, there is no medium that can live this degeneracy, okay? The medium and the other way around. If my mixing angle is different from 0, you would make it 0 by introducing matter effects. The second thing to notice is that there is a relative minus sign here. This means that there is a regime where you can hit a 0. 0, if the mass difference is not 0, this means you are hitting maximal mixing. No matter how small your original angle was, you are going to pi over 4 in matter because you are hitting a 0. This is a typical resonance. Unfortunately, life is that it's not going to be a spectacular resonance because the mixing angle in vacuum is pi over 6 to begin with, so the amplification won't be gigantic. But in principle, you have a resonant behavior, okay? So the physics is, in principle, there. But now, Okay. Now that I have the mass difference and the mixing angle in a medium, I can use all what we have learned in the first lecture and write in principle formally what is the appearance for a probability for my electron neutrino, the possibility of my electron neutrino to turn into something else. It's just the same probability we have calculated before by replacing the vacuum parameters, but the matter ones. But it's exactly the same thing. Notice that I have used the appearance probability. I have written that in a very perverted way because I have written as 1 minus survival probability. And I have done that because I want to avoid, for the time being, to discuss into what my electron neutrino is oscillating. It's oscillating into something, but for the time being, we are agnostic onto which my electron neutrino is oscillating. But let's look at the mass difference and the mixing angles in matter. There you are. The first thing you notice, although it's not especially nice written there, but the first thing you notice is that the mixing angle in matter is larger than the mixing angle in vacuum. It's very easy to see that, but I don't know why I have written in this way. If you look at this means that the sine square of 2 times the mixing angle in medium is equal to 1, let me write it in this way, 1 over 2 cosine of 2 times the mixing angle plus something. Okay, this is exactly this. But this, as you know, is the sine square of 2 times the mixing angle. This is trigonometry. This means that the mixing angle in matter is the vacuum one plus something. But the sine is a growing function, at least in the first quadrant. This means that the mixing angle in a medium is larger than the mixing angle in vacuum. Okay? It's not transparent from there, but you can get it. Okay? The second thing you notice is what we have mentioned before. There is this potential cancellation, and this opens up the possibility of 3 different regimes my neutrinos can have on the sun. The first, of course, is when the matter contribution is very, very small compared to the vacuum one. This such a way that the mass difference in matter is exactly the same as the mass difference in vacuum, and the mixing angle in matter is exactly the same one as the mixing angle in vacuum. And this is apparently what's going on with PP and beryllium-7 neutrinos. Okay, they behave as if they were produced in vacuum. We have seen this. Then you have this fantastic resonant regime. Go ahead. Because we have seen that if we replace this by the probability of creation in vacuum, F1 by cosine square and F2 by sine square, we assume they were produced as they were produced in vacuum, we nail it down to what we find for the survival probability. So, no, this is energy dependent, but they have no energy dependence. We are going to see this is what will happen in bottom-8 neutrinos. Okay, so then we have the resonant regime where these two terms cancel and the mixing angle becomes pi over 4. Unfortunately, we don't have neutrinos in the sun, which energy is exactly in this range to benefit from that. This is the only opportunity you will see in neutrino physics, at least, when nature has missed a fantastic opportunity, you know? It's a sin. I still cannot understand that, I think. Anyway, so, and then you have the the matter-dominated regime, where the matter term is the most important term, and you essentially produce a mass eigenstate. Okay, the mixing angle becomes pi over 2. And this is what's happening with bottom-8 neutrinos. We have seen that. Now this means we can understand how hard, how nice is the life of a bottom-8 neutrinos. For this, I'm going to introduce a notation that I will keep till my last lecture tomorrow, where each box represents a mass eigenstate. And the column pattern inside is how flavor is distributed in this mass eigenstate. If you want the flavor composition of this given mass eigenstate. So as I'm working only with two flavors, in principle, I should be allowed only to paint two colors. Let's say black for electron neutrinos, and let's say green for whatever is not electron neutrinos. But we have seen before that muon neutrinos and tau neutrinos almost maximally mixed. This is why I will paint whatever is not electron neutrino as half muon neutrino and half tau neutrino. And this, by the way, answer the question into which my electron neutrino is oscillating. It's oscillating to an admixture of muon neutrino and tau neutrino, almost maximal admixture of muon neutrino and tau neutrino. Okay, so my neutrino, Barenboim neutrino, is born at the very center of the sun, as essentially is born as the second mass eigenstate. All the electron neutrino content is in the second mass eigenstate. So this means my neutrino, as soon as it is born, starts leaving the sun. But while my neutrino is inside the sun, it starts having neutral current interactions and car current interactions. What an interaction does for you is an interaction projects you back into the flavor eigenstate basis. This is what interaction does. This means each time you get projected, you have to recreate a different coherent superposition of mass eigenstate. But my medium is becoming less, my neutrino is having less energy. This means that each time I'm creating a different composition of mass eigenstates. In these boxes, this means I'm sending electron-neutrino content from the second to the first mass eigenstate. What emerges is a different combination, okay? So by the time my neutrino reaches the core of the sun, already 50% of the electron-neutrino content is on the first mass eigenstate. My neutrino is not done with the sun yet, still has a lot of sun to cover. And by the time my neutrino actually leaves the sun, already 2/3 of the electron neutrino content and in the first mass eigenstate. And exactly in this way, exactly identical in this way, it arrives to the Earth. Because remember that the propagation from the sun to the Earth is effectively incoherent. So the flavor content is frozen when it leaves the sun. But so far, I have been seeing this by, go ahead. Yes, different density. And then the number of targets you find. The electron is becoming less dense. Yes, this is exactly. So this is what remember that each interaction means you are reprojecting back to the flavor basis and a new superposition of mass eigenstates is created, and it's created according to the density of the surroundings. Okay, so this is what's going on. This is a cartoon picture to explain what's going on. Go ahead. You can use both, I think. What do you mean? Okay, no, you cannot use the Dirac equation. Remember that we don't have a quantum field description for neutrino oscillations. You cannot do that. You cannot do. You can use the Dirac equation if you want a Feynman diagram associated with that, but you don't have a Feynman diagram associated with oscillation. No, we are using a contour picture. So, but in any case, for interactions, I can use a Feynman diagrams because these are standard model interactions. For neutrino oscillations, they are not described in the quantum field language, in quantum mechanical language. We lack a definition of neutrino oscillations in terms of quantum field theory. And we are, okay, we can talk about more later about this if you want. So far we have been adding up different experiments. So we seem to understand exactly what is going on with these matter effects, but we would like to be sure we are not missing anything. To get the complete picture of that, we assume the survival probability has a modulation with the energy, but we have not seen this happening on the same experiment. We have seen this happening by mixing different experiments with different systematics. We would like to see it all happening in the same experiment. Can we do that? Of course we can. This is the Borexino experiment. The Borexino experiment is an experiment done in the Gran Sasso lab here in Italy, near Rome, which was meant to measure the beryllium-7 neutrinos. The beryllium-7 are this monochromatic line of neutrinos just below 1 MeV. But regardless of whether you want it or not, you have some Barenboim contamination because you have a detector. The detector does not discriminate, it's just measured. And after Borexino is the two orange points, this point and this point. We have seen the modulation of the survival probability with the energy of my neutrino. But before leaving, I have been again misleading you a little bit. I talk to you about the solar mass pair and show you this picture, set the mixing angle. In fact, I say it's close to pi over 6. This is what I said, and I show you that. But remember that we measure only the survival probability goes like the sine square of 2 theta. This is how the survival probability goes. We have seen that. There you are. Okay, but the sine square of 2 theta is just 2 sine theta cosine theta. Okay, this is trigonometry. This will mean if I reflect my angle around pi over 4, I switch what I call sine and cosine. Okay, I just reflect my angle over pi over 4. This angle, I make the corresponding one around pi over 4. I just change what I call sine and cosine. The sine square of 2 theta won't change. So how can I be sure is this spectrum and not this one? How can I be sure the mixing angle is below pi over 4 or is just above pi over 4, the reflected quantity, in such a way that the sine square of 2 theta remains the same? And you can say, who cares, okay? Well, we care. We care because there may be something to understand there. Maybe this will shed light to the flavor problem. It won't. But we can do that. We can know it. So how we can know that? Because we know the neutrino, the mixing in matter is larger than the mixing in vacuum. We have seen this here, okay? We have seen that. And what does it mean? It means that if I look at the survival probability, remember the survival probability was the fraction of neutrinos produced in the first mass eigenstate times cosine square plus the fraction of neutrinos produced in the sine eigenstate times sine square. And this trigonometrically is equivalent to that. This means that if my mixing angle is smaller than pi over 4, the cosine of 2 times the mixing angle is a positive quantity. Okay? It's positive. But being this angle, the angle in matter, larger than the angle in vacuum, this cosine of 2 times the mixing angle in matter can have either sign. So I don't know the net sign of this term. I just ignore that. So the only thing I can know is that the survival probability is larger than the vacuum one. Final point. However, if the mixing angle were larger than pi over 4, the cosine of 2 times the mixing angle in vacuum will be already negative. And therefore, the matter term, the matter factor, will be even more negative, if you can be more negative than a negative number, okay, already. But the bottom line is that the net sign of this contribution will be positive, and the survival probability is bounded to be larger than a half. And we have seen that this survival probability is close to a third. So this spectrum is completely excluded. I know it's this one. There are way more fun things I can do with neutrinos. I detect neutrinos 24 hours a day. This means that I detect neutrinos when I'm facing the sun and they just hit my detector, but I detect also neutrinos, solar neutrinos at night, when they travel 2 times the radius of the Earth, 12,000 kilometers, before hitting my detector. Of course, for these distances, 1,200 kilometers, do not make any difference, 12,000 kilometers. However, once my neutrinos re-enter the Earth, they start having neutral currents and charge current interactions, meaning they regain coherence. If they regain coherence, there is an exchange between the flavor content between the two mass eigenstates. So I do expect to see a very small day-night asymmetry. And I do see a very small day-night asymmetry. And also expect to see spectral distortion. So the survival probability, if you want the mixing angling matter to be dependent on the energy of my neutrinos. And I have seen that. I have done also more fun things. I know neutrinos have coming from the sun because I also have observed seasonal variations as expected. There are a lot of more fun things you can do with solar neutrinos, but we need to leave them for now. So what we have learned from solar neutrinos is PP and beryllium-7 neutrinos behave exactly as they were produced in vacuum. And while high energy neutrinos, meaning boron-8 neutrinos, they exhibit strong matter effects. And these are the mass difference favored by experiments and the mixing angles. The mixing angle is, roughly speaking, we have said that is pi/6. Okay, but now again, as we have done before, we would like to reproduce this on many reasons we would like to reproduce this in the earth. First, to check we are not missing anything. Of course, this is true. But second, because we haven't seen the oscillations yet. We have seen only the flavor transitions. We would like to design an experiment where we can check that these neutrinos are actually oscillating and see the oscillation pattern. Okay, of course, these are solar neutrinos, MEV neutrinos. I can get for free MEV neutrinos from a power plant, from a reactor. Such is that neutrinos from the sun are electron neutrinos, neutrinos from reactors are electron antineutrinos. But if you believe, if you accept CPT and you believe, which is not an unreasonable approximation, I will say, that neutrinos, antineutrinos behave in the same way, you can use reactor antineutrinos to check for solar neutrinos. But now you are designing the experiment. So you have to make sure that you see the oscillation pattern. This means you are constructing your experiment in such a way that your kinematic phase will be 1. So this time you cannot miss the oscillations. So we know the mass difference is 10 to the minus 5 electron volt square. The energies involved are around 1 MeV. This means that the distances have to be 100 kilometers. If you are gonna put your detector 100 kilometers away from a reactor, you better be sure that you have several reactors and not only one of them. Otherwise, you will be sitting exactly in the right place and you will be seeing no signal. The signal dies 1 over distance square and you want to go 100 kilometers away. Okay, so this means essentially being Europe, a place where we don't like power plants, for reasons I don't understand, but this is a different subject. You have to do this experiment in Japan, okay? This one? Okay, I will go in. Okay, so I said this is the survival probability. Okay, this is just trigonometry. This is the survival probability. If my mixing angle is smaller than pi/4, the cosine is a positive quantity. Because I produce them in matter and I detect them in vacuum. I detect here on the earth. I remember, this is from the place where I produce them. I produce them in a dense medium, but I don't detect them in a dense medium. This comes from production and this from detection. This comes from production and this from detection. They are different environments. Yes. This will depend on the energy, of course, but it will be, this will depend on the energy, which neutrinos you have, but it's the same, formally it's the same formula. Yes, 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 yes. Yes.
You also had a little thing just for the same point, no? So Gabriela wrote this formula, no, that the square in matter time, say, cosine square theta in matter is just m square cosine to theta in vacuum, cosine theta in vacuum, then this 2 square root f any. This is not anymore symmetric when you replace cosine and sine. If you replace cosine and sine, it
Yes.
changes. So in this way, you break the symmetry between cosine and sine. So the inclusion of matter effect, when it is present, it's
Breaks the,
relevant to determine.
breaks the degeneracy because the Earth or the Sun is made of matter and not of antimatter. So it explicitly is broken the degeneracy between one or the other. Okay. No, the daylight asymmetry, no. I don't see this in the atmospheric neutrinos because in atmospheric neutrinos, what I see is the modulation with the distance traveled by the neutrinos. But there are no day-night effects because, I mean, if you want, there is the difference is the distance traveled by my neutrino. I have way more richness than that because I have the zenith angle dependence. So I can scale it with each neutrino coming. I don't need to do the day-night, but I have seen the same thing if you want. So there you are. Okay, so what I was saying there, you are going to place your reactor in Japan, and this is the Kamlan detector. The Kamlan detector is a small 1 kiloton liquid scintillator detector located in the old Kamioka mine, where the first Kamioka experiment used to be, and Kamlan is sensitive to 16 different reactors con distances going from less than 100 kilometers to over 1,000 kilometers, including one top secret reactor from Korea, from Pyongyang. So Kim Jong-un, we can see your neutrinos, so watch out. What I'm saying is not a joke. You know, there is a group led by Patrick Hoover trying to see, you know, these neutrinos are very hard to detect, okay, because they are weakly interacting. But this also means there is no way to shield them. You cannot shield your neutrinos. This means if you are enriching uranium, I can see that because there is no way you are going to stop your neutrinos. And there are people doing that. Patrick Hoover is one of the people leading that. He's working with the Atomic Agency to do that. There is also another group in France and in Germany, as far as I know, that they have a project, I think it's experimental group, trying to monitor the activity of the core with a small neutrino detector from outside. So that a nuclear accident won't happen because you can detect your core is about to melt by measuring its neutrinos. Okay, so there are a lot of useful things you can do with neutrinos. I'm going to talk about the other ones. But these things are happening, and there are groups active in Europe doing that. So Kamlan is sensitive to neutrinos from less than 100 kilometers to over 1,000 kilometers, although most of the signal comes from 180 kilometers. Of course, Kamlan is not the first reactor experiment to be done ever. We have been doing reactor neutrino experiments for over 40 years. This is how this started. The difference is that Kamlan is the first experiment in the right place. Before Kamlan, all the experiments were very close to the power plant, less than a kilometer, so the survival probability was essentially 1. Kamlan was the first experiment to be located where we expect the oscillation to be seen, and Kamlan has seen the oscillations. So after Kamlan, we are sure neutrinos do oscillate with a mass difference of 10 to the minus 5 electron volt squared and a mixing angle of around pi over 6. Now it's time to pull the whole picture together, okay? So we are going to talk about the reality in life. So we have two mass differences, the atmospheric mass difference and the solar mass difference. The atmospheric mass difference 10 to the minus 3 electron volt square. The solar mass difference is 10 to the minus 5 electron volt square. And when I ensemble the picture together, there are two ways of ordering them. The atmospheric mass difference on top of the solar mass difference, or the solar mass difference on top of the atmospheric mass difference. And these two orderings have a name, which is normal ordering, meaning that if you want, the way I see that is the state with the smallest electron neutrino content, the farther away state is the heaviest. If it's the heaviest, it's normal ordering. If it is the lightest, it's inverted ordering. You can also see that by looking at the sign of the atmospheric mass difference. The atmospheric mass difference understood as m3 square minus m1 square. At this point, you may wonder why I have two spectra and not four, okay? Why I don't have this possibility together with new one? Why I play this sign of inverting the sign of the atmospheric mass difference and not of the solar mass difference, okay? Which will give rise to four spectra and not to two. You don't do that because in the case of solar neutrinos, we already know the ordering. We have observed matter effects on the sun. So we already know this ordering. This is why we have two and not four. And of course, if you have three neutrinos, you have three mixing angles and one Dirac phase. You will have two additional Majorana phases, but they are not going to be present in two oscillations, but they are also there. But so we have been talking so far about two mixing angles. This is the atmospheric mixing angle, which is close to pi over 4. This will be the solar mixing angle, which is close to pi over 6. But we have a new mixing angle that has appeared, which apparently we haven't even mentioned before. But in fact, this is not the case. This is the angle with which I open today. This is the reactor mixing angle or the connecting mixing angle, theta 1,3, which we could have hinted already it was a very small angle. It's approximately pi over 20. And we already could have hinted it was very small because the smallness of this angle, together with the fact that there is a factor of 50 between the atmospheric mass difference and the solar mass difference, is what allow me to get away with by describing atmospheric oscillations and solar oscillations as two oscillation phenomena. So now that I put the picture together, I need to do, to become serious, I need to grow up and do the best values for all the experiments. So to put all the experiment together and to do a fit to all the experiments together, and I'm going to explain you why we need to do that and why we cannot. So if I put the three neutrinos, I have to use the three neutrino oscillation formula and fit all the existing experiments. This is not done by experimentalists. This is done by phenomenologists. And the reason is experimentalists only touch normally their data, never someone else's data. And this is why this is done by phenomenological groups. Basically, there are two very strong phenomenological groups doing fits. I'm lucky enough to have one in Valencia, so I'm going to use their results. But if you go to the other group, the new fit, the results are essentially identical. There is no difference between them, but this is why. This is where I get all my plots from, and you are, because it's true that they are very close friends and they make me tailor plots also. So this is why I use them. So here you have the 1, 2, and 3 sigma best fit ranges for all these parameters. You can see that in some cases you have two options, which were the two panels that I showed you before, corresponding to normal ordering or inverted ordering. Okay, so these are the two options. But if you are like me, you don't understand anything about 1, 2, and 3 sigma regions. You like to see the chi-square profiles, and there they are. So blue is normal ordering, and purple is inverted ordering. And so you can see that there seems to be some preference for normal ordering, but it's not conclusive yet. Also, you can see that although I have said many, many times already that the atmospheric mixing angle was close to pi over 4, pi over 4 is disfavored. We know already that it can be slightly larger than pi over 4 or slightly smaller than pi over 4. This, some people call it the octant problem, and the evidence seems to suggest that it's slightly larger than pi over 4. Notice also that the last angle to be measured is the most precisely measured now. Okay, theta 13 is the most precisely angle measured now. And then I'm going to talk about the CP phase a little bit more later today and tomorrow. And here you have the reason of why you need to do this in the full 3 neutrino picture. Although each of these parameters can be roughly extracted from one experiment, if you want really to be precise, you have to include the subleading contributions. There is no way out. It's not that you have a choice. If you want to get some precision, you have to do a full feed to all the neutrino experiments. Okay, so now I'm really gonna change gears and talk about anomalies. Anomalies, go ahead. I haven't said that. I'm gonna do that tomorrow. No, so far I'm working only. I'm going to talk about this tomorrow. Yes, 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 I need to do it, but I'm going to talk about masses tomorrow. So I'm going to talk now about all those experiments which do not fit, which we call them anomalies. But let me make a disclaimer first. When I entered this game 100 years ago, there were two outstanding anomalies in particle physics. One was called the atmospheric neutrino anomaly, and the other one was called the solar neutrino problem. Now, nobody talks about anomalies or problems related to solar neutrino, at least not in this way, any longer, because they are not anomalies or problems. There is pieces of new physics we understood. So some of the anomalies I'm going to mention, they may go away, but some of them may be hiding new physics that we still need to understand. Okay? So for that, let me first name the anomalies and then explain how they come about. First of all is the reactor anomaly. The reactor anomaly died last year, and I'm mentioning that just in case you heard about that. The reactor anomaly was born in 2012, I guess, when some people revisited, recalculated the flux of neutrinos you expect from a reactor. And they found that the facts that we were underestimating the number of neutrinos we expected, so that we should have seen more, but we were not seeing that. So we were missing part of the flux. This is a lesson for all of us, because how this was solved, there were two ways to calculate the number of neutrinos you expect from a reactor. One was the conversion method, and the other one was called the summation method. In the conversion method, you convert essentially the fuel you see, the reactions you measure in a neutrons spallation source or whatever, into neutrino fluxes. In the other one, you sum over all the beta branches. There are over 1,000 beta branches, and you know what happens. Nuclear data tables may be inaccurate or incomplete, so you have the gut feeling that the conversion method is less prone to error than the summation method. Okay, not that the other one is any easy, but this is what you have. And then they found there were missing 3 sigmas. In the people doing the summation method, basically nuclearists, were saying there is no anomaly. We are within 1 sigma. And we were saying, who believes in a nuclearist anyway, no? But again, the people doing the conversion method converge, and now we know that it's below 1 sigma. We call it a fluctuation and not an anomaly any longer. And this reactor anomaly died, again, natural death. Then you have the LSND, which is for me the mother of all the anomalies. The LSND stands for Liquid Scintillator Neutrino Detector. It's an experiment done in Los Alamos lab in the US. It was the first appearing experiments. Now we have a lot of appearing experiments, but that time Los Alamos was the first appearing experiments. They found small amount of electron neutrinos in what should be a muon neutrino beam, and this they ran in both neutrino and antineutrino mode. The signal they found was stronger in the antineutrino mode, was weaker in the neutrino mode, but it was in the, let's say, 3, 4 sigma ballpark. This experiment was extremely controversial for its own reason, and because the collaboration split over this result. So the collaboration, half of the collaboration was behind the result, half of the collaboration was against the result. This is what it was born extremely controversial. And then we decided to make another experiment I'm going to talk about to prove or disprove the LSND signal. And the last anomaly is the gallium anomaly. The gallium anomaly is the underdog of all the anomalies. And I am sure it's the underdog because for many, many years, it didn't even make it to the list of anomalies. We completely ignored that. But the, the common factor between all the anomalies we have is that this, if you want to explain this with oscillation, you need a mass difference of the order of 10 to the minus 1 electron volt square. And you know what happens? If you have 3 neutrinos, you can only choose 2 mass differences, okay? The third one is just the sum of the other two. And we have an atmospheric mass difference, 10 to the minus 3 electron volt square, and a solar mass difference, 10 to the minus 5 electron volt squares. No matter how creatively you add these two numbers, you will never make it to 1, to 0.1. So if you want to explain this with oscillation, it's unavoidable that you need new states. You need sterile neutrinos. So what happened with this anomaly for the LSND? As I said, a new experiment was set up at Fermilab, which is called Miniboon. LSND was a very short baseline experiment, 30 meters, 42 MeVs. Miniboon is half a kilometer, half a GeV. So it's completely different experiment, but the L over E is essentially the same. So they are checking exactly the same oscillation region. And unfortunately, Miniboon has its own mess. Was not able to prove LSND, but was not able to rule out LSND either, because it has its own anomaly in a different place, and this anomaly is at the 5 sigma level in the neutrino run and not in the antineutrino run. So, but you know, mathematics is a very elastic subject, so you still can do a fit to both experiments and you find a minimum, okay? I mean, your likelihood is convex, so you always have a minimum, but the minimum where you have the minimum, which is in principle compatible with LSND and Miniboon, if you look at it, the chi-square per degree of freedom, you see it's close to 2, meaning that the two data sets are completely inconsistent with each other. Besides, this is excluded for other experiments. So what do? We set up a third experiment, okay, to sort out these things for good, which is called Microboom. Microboom is part of the Fermilab short baseline neutrino program consisting in 3 detectors, 400, 600, and 1.2 kilometers. Microboom is one of these experiments. So, but do not hold your breath. It has been shown that there is a blind part on the parameter space for Microboom where they won't be able to rule out LSND or Miniboom if you want. So maybe the situation in 10 years from now is still unclear. I don't think so because we have 3 detectors, short baseline experiments. So probably the situation will be sorted out before what we expect. Okay, so let me talk about the gallium anomaly. The gallium anomaly comes from 2 different experiments, 2 runs each. For you to see how old this experiment is, SAGE, which is the second of this experiment, stands for Soviet American Gallium Experiment. If it's called Soviet, you already know how old this is, but the lesson is there was a time where Americans and Soviets were able to collaborate fruitfully, and this may happen again, you know, hopefully. Okay, but you already know the name of the game. The name of the game is to calculate the number of neutrinos you expect. Here, this will mean to calculate the cross-section of your capture process. Okay, this is the capture process, and once you do that, you see that discounting all you know, you are missing 15% of the signal. So what do? We say we have a problem? Of course we don't. We say, we look at the nuclear physicist and says, you did it wrong again. Okay, you have overestimated this cross section. What you have to do is to go back and calculate it again. And watch what you wish, because they did that. And the situation got only worse. So The final result is we did a new experiment, which is the best experiment. BEST stands for Baikal experiment on sterile neutrinos. And amazingly enough, we did this experiment 30 years down the line. The error bars shrunk a lot because you have way better technology now, but the central value remained. So your problem is now 5 sigma. Okay, but the good news, I'm not sure whether the good news is you cannot explain this away with oscillations. Oscillation will require too much large a mixing angle. But you have a problem there, which may be related to new physics, might be something which will go away. I doubt it, but it's there to be explained. But if you try to play the game you have been playing before, this means blame the nuclearis. This time it won't work because it has already been shown that if you change the cross section, the significance won't go away. You can lower down a bit the significance, but it won't go away. So this is something that should worry us a lot. It worries them. It should worry you as well, okay? So now let me introduce another politician, probably as successful as these ones, which is called Donald Rumsfeld. You probably never heard about Donald Rumsfeld. Donald Rumsfeld was Secretary of Defense of the US when George W. Bush was president of the US. The US, as always, he was involved in several wars, okay? This is the US, okay? He was not especially successful as Secretary of Defense. However, he defined, for me perfectly, what is doing phenomenology all about, okay? And he said, there are things you know. There are things you don't know. But the most interesting things are the things you don't know yet. The unknown unknowns. And this is what we are going to do now. We are going to navigate the Rumsfeld matrix. So we started by knowing all the things we know. Now we are going to move to the things we don't know yet and would like to know in the next coming years. And then we are going to speculate, because you can only speculate, what are the things we don't know yet. What can come about. So you can do your list, but my list of the known unknowns, for me, the four most pressing issues in neutrino physics are these ones, which are, the first one, of course, is whether neutrinos are Dirac or Majorana particles. This won't be explained by the oscillation program. They need dedicated experiments. We will talk about these experiments tomorrow in the morning. The second question is whether there are light sterile neutrinos out there. We don't need, there is nothing we need them to explain, but they can still be there, and we need to go and search for them. The short baseline program will cover part of it, and also the long baseline program as well. I'm going to talk about a little bit. You will hear more about this afternoon. And the third program is what is the mass ordering, whether the spectrum is normal or inverted. I'm showing this in terms of the CKM matrix. You have seen that the mixing matrix, the CKM matrix, in the case of quarks, is pretty diagonal. Okay, it's very, very diagonal. It's not diagonal in the case of neutrinos. In the case of neutrinos, this mixing matrix is called the PNMS matrix. Okay, Pontecorvo, Naki, Masaki, I don't know it. Yes, it's called the PNMS matrix. And so what we saw before, what means normal or inverted ordering, remember I said whether the state with the smallest electron neutrino content was the heaviest or the lightest, or whether the sign of the atmospheric mass difference was positive or negative, can be translated into this matrix as the smallest entry of this matrix is the 3, 1, 1, 3 or 2, 1, okay? This is the question, and of course, whether CP violated in the leptonic sector. So how we are going to answer these questions? Let me go, what is the neutrino mass hierarchy? I said before in my first talk, my first lecture this morning, I will keep saying many, many times, that the physics we have here is the same physics they have in the case of quarks, the electroweak part, I mean. This means that all the questions we are answering now, they have already answered them. So the only thing we need to know is to see how they have answered to the same question and replicate that. And of course, this is what we are going to do. Everybody knows by that. by now that the mass of decay long is larger than the mass of decay short. This is very old knowledge. It's knowledge from the 70s or 80s. How they did find out this? They pass kaons through matter, which they call a regenerator. And they have beaten the unknown sign of the K long, K short mass difference with a known sign of the regeneration amplitude. They mean they have created an interference between these two terms. And by seeing whether the interference is constructive or destructive, they see the relative sign between the two terms. But knowing already the sign of one of the contributions means you already find out the sign of the second one. What we are going to do? Exactly the same. Okay? So we are going to pass neutrinos through the Earth. Okay? Our regenerator will be the Earth. And we are going to beat the unknown sign of the atmospheric mass difference with a known sign of the electron electron forward scattering amplitude. Okay, we are going to do exactly the same. We have one advantage and one disadvantage. Okay, the advantage is that neutrinos are weakly interacting particles, which, by the way, is also a disadvantage. But the advantage means that you essentially do not need pipes to send your neutrinos. You shoot your neutrinos one side of the Earth, and they emerge the other side essentially untouched. Okay, so for us, it's way easier to do experiment. The problem is, again, neutrinos are weakly interacting particles. If I want to pile up these experiments, I need my neutrinos to cover very long distances, again, of several hundred to 1,000 kilometers. But of course, I have those baselines, and I can do that. So if we go back to our list, how I'm going to show whether CP is violated in the neutrino sector? I said before that this phase is the same as the one you have in the quark case. Okay, so we are going to do again what they have done. How do they know the phase in the CKM is different from 0? And I'm going to do exactly the same. Remember when you were taking your undergraduate courses, they talk to you in the case of quarks. What are the 3 ingredients you need in order to find CP violation? All the quark masses have to be different from non-degenerate, let's say. All the mixing angles have to be different from 0, and all the 3 families have to be involved. The same is happening here. Let's see how. The difference for us is that you need all the mixing angles to be different from 0 because everything will be proportional to the Yarsloch invariant, which is the product of all the angles in the space. But the Yarsloch invariant, which was a strong suppression in the quark case, because remember, this matrix is very diagonal, it won't be such a suppression here, because our matrix is not diagonal at all. So what we are going to do is exactly what they have done. We are going to look at the appearance channel. Remember that I cannot look at disappearance because of CPT theorem. This appearance in both channels is forced to be the same. So I have to look at the appearance channel and compare what I see in the neutrino case to what I see in the anti-neutrino case. And any difference will be exactly CP violation, which is, of course, proportional to the Yarsloch invariant, as you expect. But notice that now is proportional to the sign of all the 3 kinematic phases as you expect, because I said all the 3 families have to be involved. But notice that now is proportional to the sign and not to the sign square as before. This means that if the oscillations are too fast, they will average to 0 and not to a half, as in the case of oscillations. So you have to trigger the 3 kinematic phases, but not much. Okay, but again, this means you have to cover very long distances, because these two, I agree, they are essentially identical, but there's a factor of 50 with this one. And if this one is 0, it kills the whole project. Okay, so you have to have them all triggered a little bit. And again, this means you have to send your neutrinos through very long distances. But remember what I said, we don't send neutrinos through pipes. We send neutrinos through the Earth. But the Earth, we have seen in the solar case, is matter-antimatter non-symmetric. The Earth contains electron, but not contain positron. So this will break the degeneracy between neutrinos and antineutrinos and will induce a difference between the neutrino-antineutrino channel, which is the matter effects. So it's a fake matter-induced CP violation. Even if this phase were 0, you will still have a difference because you are seeing matter effects. You are seeing that the Earth contains electrons and not positrons. Okay, and we have seen before in the sun that matter effects flip sign when you go from neutrinos to antineutrinos. This sign flipping is what you are seeing here, but you are targeting this term. So how you are going to do that, and in fact there are two strategies to deal with, let's say, matter-induced or fake CP violation and true one. There are two, I'm going to call them the Japanese strategy and the American strategy. And okay, so the Japanese strategy is, if you ask, is very Japanese, okay? It's super Japanese, which is if you have problem with matter effects, keep them small, okay? Keep them short. This means you go to short baselines. Short baseline we have seen, 230 kilometers, okay? But then do something very, very radical. So point your beam somewhere and place your detector somewhere else, 10 kilometers away, off axis. And although this looks really crazy because you miss most of the signal dies 1 over distance squared, it can be shown that the neutrinos you get in the off-axis detector are very low energy neutrinos, and you get almost a monochromatic beam in the off-axis detector. And for this particular window of low energy neutrinos, you get way more statistics than the one you would have gotten for this particular window in the on-axis beam. By the way, the idea of going off axis is not Japanese, it's from the US, from a scientist at Fermilab. But then what you gain is that L over E remains being what it used to be. So you reduce the L by going short baseline, but also reduce the energy in such a way that you still can place yourself in the first oscillation maximum. This is the Japanese strategy. The American strategy, again, if you ask me, is very, very American, okay? So you cannot deal with matter effects, just embrace them all. Go very long distances, a la American, okay? 1,200 kilometers, the Dune experiment. But then, okay, get a non-axis beam and tons of data. If you get tons of data, by the spectral distortions you get from one term and the other are different. From the spectral distortions, you will be able to tell one effect from the other. This is, I will take 10 minutes more. I will try to be fast, okay? So this is their plan, but what can go wrong? What are the new physics that can appear? I will be very, very fast. First of all, you can have sterile neutrinos. You will hear more about sterile neutrinos later. This is the muon neutrino survival probability we have seen. If you have one more additional sterile neutrinos, how many mixing angles and how many phases you have? You have, with only just one sterile neutrinos, we have done the calculations, you have 6 mixing angles and 3 Dirac phases. However, life is generous and simplification exists. And this is in the most simplified scenarios, you can get away with 2 mixing angles and 1 new mass difference. And this is the way you change the muon neutrino survival probability. And this is what you expect to see. This is a very complicated plot. Let me walk you through that. This is the probability. If it starts in 1 is survival probability. If it starts in 0 is appearance probability. These experiments do not rely on, they want to be precise. So they don't rely on the calculations of the number of neutrinos they expect. They have a near detector and a far detector in order to cancel systematics. So the gray lines are what you expect to see in the near and the far detector. And above I have the true neutrino energy going the other way, okay, left to right. So you don't have to look at it all. Let's see about, if you look at the black line, this is what you will see if there are only 3 neutrinos for the muon neutrino survival probability. The blue line is you would get if you have one sterile neutrino with this mass difference. If you increase the mass difference even further, both the far detector and the near detector get a lot of sensitivity. Yes. Okay, so only 5 minutes. So you can see, you will hear more about sterile neutrinos in a while, but you will be able to see that. But what would happen if there is a sterile neutrino out there, but you cannot oscillate into this sterile neutrino? Phase space into oscillation is closed. You cannot produce on-shell this sterile neutrino. Are you going to miss that? Of course you are not, because you are going to see these as violations of unitarity. Your mixing matrix, your true mixing matrix, the one which is going to be unitary, will be 4 times 4. So when you are looking at your piece of it, it's going to be non-unitary. So to discuss non-unitarity, we need to need unitarity first. So if you have a mixing matrix, unitarity, the only thing that it means is that U dagger U is equal to 1. Okay, this is being unitary. If you take the first equation not equal to 1, the 1 is 0, when the two leptons flavors are different, this is what you get, okay? L is 1 lepton and L prime is a different lepton. If they were the same, they will be 1 here. So if you divide everything by these factors, so if you divide everything by these factors, so you have some complex number 1, some complex number, these are 3 numbers adding up to 1. In the complex play, you can draw a triangle. This is as they do it in the case of quarks. In the case of quarks, they have the unitarity triangles, and you know that the area of this triangle is just the Yarslock invariant. So these sides are the two this, and you have 3 angles which are related to that. Okay, the way we have been doing non-unitarity searches in neutrino physics so far, it's just by looking at the sizes of these angles. But you know what happened? What we are doing is to see that we have 3 sides that can make a triangle. But we are not testing they actually made that. We are trying to rule out unitarity. We are not at the point of proving non-unitarity yet. And there is a strong difference. If you look at this here, I'm keeping the 2 sides of the two sizes of the 2 sides constant. So they could form potentially a triangle. But how do you know they are actually doing that? We need to move in neutrino physics from checking the size to checking the angles. The only way we will be sure that there is unitarity or not unitarity there is by checking the angles, not the sides. The sides allowed us to rule out unitarity if there is no way of closing the triangle. But maybe the triangle can potentially close, but it's actually not closing. Who knows that? You have to check that. So how we introduce that? We introduce that in this way. If you want to keep the parameterization you have been using, you have to introduce violations of unitarity in this way, where the diagonal ones, of course, they are real, but these ones are not necessarily so. And then you can bound these parameters for many, many regions. In the sake of time, but if this, remember, this non-unitary game is essential, because in order to extract CP violation, I already assume that my mixing matrix is unitary. I extracted all the information I'm going to use to discover or not CP violation, assuming unitarity, but I haven't tested yet to this level. So there is a dangerous game going on there. And tomorrow more, okay?